So when we talk about recursion in general, we imagine a function that computes something and then calling itself again. But how do you design a recursive solution and how do you think recursively? Hi, I'm Piyush, and in this video and the next couple of videos, we are going to discuss a powerful strategy called the recursive leap of faith, which will help you design recursive solutions using first principles effortlessly. Over the next few videos, we are going to discuss a few set of LeetCode problems, dynamic programming, and by the end of these videos, you will be designing recursive solutions like a pro. So open your notebooks and let's get started. So let's start with a simple problem. We are given an array of numbers and we need to find the sum of the elements in the array. The obvious answer is that we can simply iterate over each of these elements, right? Well, that's great. But what if you already have the sum to some part of the array? In that case, you can simply add it with the remaining element and you're done, right? Now pause for a moment and understand what this actually means. What if you already have an answer to the sum problem? Can you use it to solve a complete problem? Let's say this answer to the subproblem or the sum of this part of the array was given by a function findSum. We can simply do the same again, that is add the remaining element 2 in this case and find the result. Now do you observe the strategy over here? We can actually pass the entire array to the same function which finds the result of the entire array using the result of this subproblem. The key intuition here is that if it works for n-1, it will work for n as well. Now before we jump ahead and understand more about the strategy that we just discussed and solve more problems using this strategy, let's first trace the recursive calls for the function that we just wrote. So we start by passing the entire array to this method, and at every recursive step, we pass a part of the array to the same function to solve a small part of the entire problem. At the end, we will be left with just one element that is passed to the function. Now this is the smallest subproblem that is possible. This is also called the base case, and we don't need to divide this again. And we can simply return a sum of 2 in this case. Going back to the recursion tree, we can now see how the sum is calculated by using the solution from each problem starting from the base case. And finally, we got the sum we wanted. Now this was a pretty simple example with a pretty simple solution. And this was just to give you an intuition of what recursion actually looks like and how to trace function calls. And now we are really ready to understand the strategy behind designing recursive functions. Now, if you have noticed, tracing function calls or tracing recursive calls might get overwhelming, and instead we're going to focus on designing a strategy for devising recursive algorithms faster and in an effortless manner. So let's jump into the strategy. But before that, let's look at the most simplest recursive paradigm with the strategy or the ideas that we have discussed so far. For any recursive function, we'll have a base case which simply evaluates the smallest subproblem if that subproblem cannot be divided further, or else we divide the subproblem into smaller subproblems and then pass it on to the recursion, or as we commonly say, we solve it recursively. We will now discuss a step-by-step approach for designing recursive solutions, and we will also look at the recursion tree to understand how everything fits together. We'll also briefly talk about backtracking and divide and conquer algorithms in this video series, but the main essence of this video series is to give you an idea of how you can devise recursive solutions and dynamic programming approaches using first principles using this recursive leap of faith strategy. So let's get started and see what the strategy looks like. Let's now understand the design method for recursion. We'll start with the findSum problem, and we'll later use the same strategy to solve a more complex problem. Let's visit the prerequisite step before we actually start framing the solution. Now this is the most critical step as we need to investigate all possible subproblems and then select a way to divide the subproblems or divide the problem into simpler subproblems that can be solved independently. In this case, we can either divide the problem into a subproblem where we find a solution for n-1 elements first and then add the remaining element with the result from the subproblem, or else we can also divide the n elements into two independent subproblems that will be solved recursively. We will later see that this second approach is a classic divide and conquer approach. Well, that's a story for another day. The main intuition we need in order to divide the problem into subproblems is that we want to know if the answer to this subproblem can help us solve the uber problem by combining the result from the subproblems. Cool. We will use the first subproblem dividing strategy for this particular example since we are already familiar with it. Let's now move to step 1. Now this step is the most simplest step, though the most non-intuitive as well. We'll define the function and the input parameters and what it's supposed to do. To rephrase, we must define what result we expect from this function with well-defined inputs. For the find sum problem, this is simple as we can simply define it as find the sum of the elements from 0 to n given the input array. In almost all problems, this step will be quite simple as it will define the problem that you are trying to solve. The next step in the design process is where all the magic happens. We will deep dive into this in more detail in the end of this video as well. This step tells us that if it works for n-1, it should work for n as well. Now this is also where we have to take the recursive leap of faith to recurse onto the subproblems. So if we take the recursive leap and recurse onto the subproblem we identified before, that is the sum of n-1 elements, with the faith that this method will correctly give us the result. Now we are calling this step as recursive leap since we have not yet completed the entire function, and the most important part of this step is to assume for now that this function will definitely work for n-1. Now the third step, the inductive step, is where we use the result from the n-1 subproblem and use it to solve for n. In this step, we basically combine the results from the subproblems to find the result of this problem for n. In this case, we can simply add the sum from the recursive call to the nth element and then return the result. We can simplify the operation and combine it in a single return statement just for simplicity. Now the final step is where everything ends. We solve for the smallest subproblem, the base case, where we identify what we should do for the smallest subproblem. In this example, the smallest subproblem is when we have a single element and we return the element itself. Well, this sums up the intuition and the recursive paradigm for designing a recursive solution. In the next video of this video series, we'll discuss more about how to use this strategy for solving more complex problems. But before that, let's check out how the computer actually tracks recursive solutions using a recursive stack. Now in general, a particular function will have multiple instructions. For simplicity, we can break down this function into two instructions, which will be part of the call stack. Whenever we call a function execution context is added to the call stack, and this context has information of the next instruction to execute when it runs. And as we call each function recursively, we keep on growing the call stack. Now, as we discussed, each execution context stores the next instruction it should process. So when a recursive call returns, the function can carry on with the next step. Now, once a function returns, the result is returned to the caller and the execution context is then popped from the stack. The execution context on the top of the stack starts executing based on the result of the recursive call and so on. So when you're designing a recursive solution, you must also keep in mind the space taken by the recursion call stack while calculating the space complexity. Now that brings us to the end of this video. In the next video, we're going to discuss a more complex problem where we're going to use the same strategy to build a solution and then explore the time and space complexity and how to deal with such complex problems as well. Cool. So if you like this video, do share it with your friends, do subscribe to my channel, and see you in the next video. Bye.